Okay, we're ready. Okay. So it's our pleasure today to welcome Luca Di Mascolo. Luca got his PhD in 2020 from the Max Planck Institute for Astrophysics in Garching, where he worked under the supervision of Rashid Sunyaev, Eugene Chuladov, and Anthony Hare. And he then moved to Trieste, Italy, for a postdoc with Alessandro Faro to work on submillimeter observation of galaxy protoclusters. In 2023, he moved to Nice in France, where he collaborated with the ICE-CSIC France team on the high-frequency science development. In 2024, he moved to Kapteyn Astronomical Institute in Groningen as a research fellow. And broadly speaking, he's involved in several collaborations, like submillimeter facilities, such as Atlas, Simon, the South Pole Observatory, and he's interested in the evolution of the intracluster medium, co-evolution of galaxies and the environment, statistical data modeling, and also sonification. Well, the floor is yours. Thank you for coming.
Thank you very, very much. And the thing I want to also say, like, first, feel free to interrupt me and to just make this a bit of an interactive talk. Yeah, thanks all for the introduction. Actually, it's actually covering a bit of like what I was going to talk about during this talk. As you see from the title, I'm interested in the hot side of things in the universe. And before start digging into that, I want to start from actually an image. This is like from a simulation. What we're seeing here is the galaxy clusters, and specifically you can see like the two BCGs, like the brightest cluster galaxies are interacting. This is a merging system, and this of course is the stellar distribution like inside this cluster. These are like telling a lot of information, specifically like about the dynamics and the stage of these, this evolutionary stage of this system. But what's more interesting is that if we simply change the way we're seeing at the systems, we'll start to see that this actually is much more around the star. This is a map from the same simulation of the hot gas, well, the gas and the temperature of this gas around those BCG. Thing is like basically the volume of clusters, but also in terms of large-scale structures of the universe is really filled of very hot component. And we see like around, if you just go even beyond the Sol galaxy cluster volume, we start to see we have all these very extended regions of hot gas, and mostly like, well, void, you can just see from the optical perspective. So we can kind of say that the universe is hot. And if you go to see, for instance, like the amount of gas we have in the universe in a specific system, for instance, these are like, once again, from simulations. On the left here, you see the amount of gas that is inside galaxy clusters progenitors. When moving like from high redshift to low redshift, and in red, you see the hot gas. You see the really round redshift tree. The hot phase starts to be the dominant contribution to the overall mass budget of a galaxy, baryonic mass budget. But also if you move to, for example, like galaxy scale, and we see here like, like the evolution with the mass of the halo, we see that the hot CGN is in green, is always like somehow dominant. So if we really want to understand how the systems evolve, we have to go and check basically like what's the happening on the outside. But it's not just a matter of like quantity, it's also a matter of like information we can get. So the hot phase of like cosmic structures really encode a lot of information on the evolution and all the processes that drive the thermal evolution of the systems. Once again, this is like from like a very basic perspective on simulation. Here on the left is once again emerging galaxy cluster, and we see that basically depending on when we observe the system, we have completely different structure. Like in the very hot component, for example, here is like structure, but also we have very complicated velocity structure. We can actually measure to understand, for instance, turbulence and how this can impact the thermalization features. But if you move, for instance, also to the very core of the systems, this is like a comparison of two different simulations of AGN in the center of a galaxy cluster, depending on the specific. Okay, this is like depending on the specific assumption for doing AGN feedback. Also, it's a subgrid models. But the point is that we can really distinguish which one is actually impacting like the more or less simply checking what's happening on the hot component. And so this means that basically if we go there and study that, we can actually have a lot of information on, for example, like AGN feedback modes. This is a brief introduction that is all based, of course, on simulation. So the next question is, what is observation telling us? So of course, studying hot gas in the universe insists on so much, and it means also studying a lot of different environments. For preparing this talk, I thought okay, I would just take basically an approach that basically kind of follows my path into the hot gas, and we'll start basically from galaxy clusters. This is not good. So I mentioned galaxy clusters already, but the main point and the main reason why it's really good to go there to study the gas, because these are the largest gravitationally bound objects that we have in our universe, which means also they kind of resemble the universe itself in some sense, in terms of baryon fraction and also properties. This is just a nice image to introduce to the topic. Here you see specifically is an HST image in the background, and this kind of faint cloud is basically the intercluster medium that is filling the entire volume of a galaxy cluster. It's very hot, talking about 10 to the 7, 10 to the 8 Kelvin gas. What do we know about this? Quite a lot, actually, right now. And everything is mostly being driven by X-ray measurements of this gas. So, for instance, we know that through cluster mergers, as also showed before, we have the generation of these large-scale shock fronts that can really heat up the gas inside the clusters to the temperature we see in local systems. And it's a very famous polar cluster. But also we learn a lot about, for instance, the cross-section of dark matter. We learn that turbulence has a very important role in defining the thermodynamic structure of clusters, also the survival of the structure of the systems. You basically add some pressure support so we can sustain that. And this basically combined with the effect of AGN feedback that I already mentioned. But for instance, here you see a very nice comparison of a radio jet in red, and in blue is the X-ray observation of the system. So we learn by comparing radio and X-ray that this radio jet can really push out the gas and really heat up through mechanical heating the cluster medium, which means basically it can sustain what could instead be like a catastrophic cooling of the whole gas through emission. And then finally, of course, we also managed to get a bit of understanding of the large-scale structure of the universe, also really get into measuring and observing this very faint ridges of gas that basically exist within clusters and galaxies. This is a very nice picture, and this is mostly, as I say, this is based on X-ray measurements. But there is one specific thing that I'm hiding here. It's these are all very nearby objects. Talking very close, below redshift 0.5. If you really want to understand how the hot gas evolve and how the structures evolve, we really have, of course, to extend our perspective well beyond limitations of current observations and go to high redshift. So just a poll. What is the definition of high redshift for this audience? So below 0.5, can you raise your hand? Okay. Between 1 and 2, above redshift 2. Okay. Well, I don't know. My definition of high redshift is between 0.5 and 2. Okay, so roughly, and of course, if you go to 2 over 2, yeah, that's no, that's not even something I can measure right now. Okay. The problem is, if you go to redshift 2, what happens? That this is what an X-ray observation looks like. It's great. To be absolutely honest, this is an amazing observation of redshift 2 galaxy cluster, but it's not as detailed as the images I was showing before. So we need something else. So the reason why this is happening clearly is just limitation of the observation we're considering here. Just to give you a reference, this is the distribution of galaxy clusters and groups that have been observed with eROSITA, so through X-ray survey. And you see that basically as any emission, as you go up in redshift, the limit goes up because of course you have cosmological dimming. We have to find something that really can bring us to actually observe these regions here easily. And this solution is called Sunyaev-Zeldovich effect. I'm pretty sure, like, having Tony around, you might have heard about it already. A bit of context, what it is. So the idea is that you have CMB in the background, and the CMB photons are interacting with the electrons that are in these large reservoirs of hot gas, which means they're doing inverse quantum scattering. And this is, for instance, an image of a galaxy cluster in the SZ. The very cool thing is not just that this actually has interesting consequences for what we can do. First of all, is that given like the way we're measuring, this actually is providing the SZ effects, providing a direct measurement of the thermal energy of systems. Going back to what I was showing in the beginning, this is very important because we really understand how much each process is actually contributing to heating up the structures. I will go to the last one first and then go back to the central one. Has a very peculiar spectral property that I will go back to, but this means that we can actually measure it very easily. But the most important part is like, is it basically like acting as a shadowing effect on the CMB? And CMB is always at the same redshift, as far as I know, which means basically the effect we're measuring doesn't depend on the redshift itself, or at least, of course, if you factor out like the evolution of systems. Something very important as well, and this is mostly for if you're interested, for example, like in cluster cosmology, the SZ is not measuring realization in any way. They're actually measuring thermalized gas, which means actually even if you have like filament or like a random collection of like electrons, and they're in thermal equilibrium locally, we can actually measure it. So, and then of course we can introduce realization assumptions for converting, for example, SZ measurements to mass of clusters and then doing cluster cosmology and so far so forth. Why I mentioned this, so spectral property, it actually is a very cool, very useful tool because it has a very peculiar like spectral signature. So just here, like just a bit of reference, this is like the CMB, and this is the SZ CMB. So like the inverse quantum scatter CMB. If you just take the difference of the two, we'll get the banana yellow curve. What's very interesting is that basically you have that below this frequency, you have something like an absorption line, but in continuum. And this is the only process that can generate like a negative, like a decrement in the CMB surface brightness over this like broad range of frequencies. I don't know if you can see it's a bit small, but this like goes to 100 gigahertz to like 1 gigahertz, 10 gigahertz. And then of course we have a crossover, and we have an increment, and this is how things will look like if you just take a map. So we have basically just noise or CMB. Here, basically it will be like a galaxy cluster. So we'll see kind of a hole in CMB, and then of course like emission on the other side. Something I want to mention, just to also give an idea of how powerful this can be, is that it's not just redshift independent. But what I've been talking about and what I will be talking about mostly is actually the thermal as the effect. So just one specific component that connected to the thermal motion of the electrons. It's not the only one. You actually have one specific effect, so the kinetic SZ is measuring like the curve velocity of the systems or part of systems and density. So we can actually get the two information together, but also we have relativity corrections that basically depends on temperature. So if we combine all these things together, we have a complete picture of the thermodynamics of the systems, which I've mentioned already. To me, it's very important. So how can we use this? For instance, since it's redshift independence, to find clusters, first of all. So this is the thought I was showing before. If we add on top of this, the Z measurements, this is what we'll have at the moment. So this is a collection of all the clusters we have identified in large-scale surveys with the SZ effect. This is like Planck, and SPT mostly. The most important feature here you can see is that the selection of this cluster is completely different from X-ray and actually goes perfectly down. And this is just a consequence of the fact that we have no redshift limitation. So in principle, we could even go even further down, but then of course we hit the mass limit on the top, like IMAS end. And what's the first thing we can do? Of course, we can count them, but also we can start to study them and to study how they are in terms of thermodynamic structure. The first thing is to go and measure like using the thermal SZ, which I was mentioning, and for example, to get the information on pressure. This has been done quite a few times, and it's like a collection of all the samples that have been used and regimes and range in terms of redshift and mass. what we found is that pressure distribution is incredibly self-similar. So basically, all the clusters follow an average one. So like, so they're kind of boring on this side, but also very interesting. Very things. To me, what's interesting though, and also is not actually the average probabilities are, but actually what are the deviations from that. If we start to see and actually measure the scatter around this average, we see that we have basically this trend. This is like from a specific period by series, 2003. First, we have like a small radii regime where we have deviations from this subsimilar scaling that is mostly driven by like internal dynamics and also a giant contribution to the thermal structure, and in general, like also supernovae feedback as a whole. And on large scales, we're having still like everything that connects to more like cosmological evolution and low thermalization of the gas inside the cosmological, the gravitational well. If you want to understand how these things evolve, my view is that we have, of course, to really characterize what is driving these deviations from the average profile. It is not just gravity. But of course, if you want to do that, we need to really start resolving the clusters. And this comes a bit of a problem. So this is a cluster in observed in a Z with Planck. And I want to ask you another question. It is, can you recognize which cluster is this? If you do, please raise your hand. Yeah, except Tony. I'll add like a hint. This is a higher resolution observation. This is a NACT measurement from Atacama Large telescope. So we have roughly a factor of 10 improvement. Any better chance? Okay, I will help you. I will do a quiz. So we have a Perseus, the bullet, or Maxwell 717. Who's going for the Perseus? Raise your hand. Okay. Who's going for the bullet? And who's going for Maxwell 717? Okay. So we have 1, 2, 1. The others are things that it's another cluster. So drum roll, it's the bullet cluster. So this is kind of like showing that the problem is like we're really limited in the information we can retrieve from the general like SZ measurements. So we have very low angle resolution, but there's an interesting aspect here. This X-ray measurement is immediately measuring the very core of this cluster, just completely losing information on large scales. Actually, it's an extra benefit of using a Z compared to X-ray. We can really go towards the outskirts of these structures and learn a lot about them. Fast forward today, fortunately, we improved a lot in terms of angle resolution. This is Planck, just as a reference, and this is F that was showing before. And now we have, for instance, RM, we have maximum 2, and ALMA. And this is actually in the upper limit of the angle resolution we can get. With ALMA, we really improved a lot and in terms of like what we can achieve. Instead of like going into the details, I want to show what we can do, for instance, just with a few examples. And I want to go back to the bullet specifically. So this is a bullet cluster. This is a merging system. The reason why it's called the bullet is for this feature here, it looks like a bullet going through here, just causing a bow shock. And for context, this is the shock front, and this is just the subcluster is like really injecting the like energy and just inducing the shock. One of the key questions is what is happening at the shock front in terms of like plasma physics, and specifically from other systems, and there's like a collection and systems in general. We know that at the shock front, electrons and ions basically have different temperatures, and this because basically the equilibration to the standard shock conditions as they happen through Coulomb reequilibration. So it takes some time. Just to explain a bit, so what happens is that you have a shock front. So the electrons get given up by adiabatic compression first, and the ions as well, but then they slowly reequilibrate, with time. And this is something we observe in a few galaxy clusters. You can see here, like Able, but also of course like a bullet and Hanniverse 1. What happens though, if you actually go to the literature, we have contradictory information, because actually there are a few systems in which we see there is like a fast reequilibration of this temperature. And this particular, for 3 of these, for 2 of them, we have inconclusive results. The problem is that we don't know what's happening, and we don't know which was the right scenario. And if this is happening specifically, we don't know what is causing it. there is an interesting feature, if you notice, that is actually the bullet is appearing twice. The reason is this measurement here was obtained using X-ray observations, and this one here was obtained using SZ and X-ray observations. Basically, what we're doing with the SZ measurements with like very high angle resolution, we're talking about 8 kiloparsec resolution in terms of like physical scale. We're basically circumventing a big problem in X-ray measurements. That is limitation in temperature we can measure. It's a shock front, so the gas is boosted like well beyond what we can measure with X-ray telescopes. And basically for Chandra, this is like hot gas, whatever. With SZ, we can actually complement information and get like very precise constraint. Why this is important is actually if this is the case, we can immediately we're measuring the wrong pressure, and which means we're measuring the wrong thermal energy, and then means also like the wrong mass, which goes into of course like wrong cosmological constraints from SZ measurements. And there are like evidence that is happening also in the outskirts. This is just a very simple plot, but it's like showing this like a deviation here that is like where like we expect to see accretion shocks. Once again, if this is confirmed, it means basically like our measurements can be extremely biased. So we have to really go there and improve our understanding of thermodynamics. This is where we are right now. So there might be something to do. But going back to what we can do in terms of like also combining X-ray and SZ, this is for example like a very nice example. Going instead of going towards shock fronts and the outskirts, going to the very core. So this is actually a cluster showed before, the one like with the AGN like radio jet, kind of like sustaining the structure. So you can see here like these cavities that are basically inflated by the radio jet. What's very interesting is that if we add on top of this radio contours, so we see that the agent like it's treating like these radio jets and just filling the cavities with the radio emitting plasma. What this plasma is, we actually have no idea yet. Well, we have clues, but we added on top of this SZ measurements. So this is a map we obtained with Mass-Time2, and the first thing you can see is that we exactly see the same structures. Actually, this is an amazing measurement in terms of like what we can achieve in terms of SZ, and it's moving quite, of course, beyond what I showed, for example, like with Planck and active measurement. What we learned from this, a few things. So first of all, is that we managed to understand like how much this gas is suppressed. The problem is that in X-ray that we cannot measure what's in there. With the SZ, we actually can. And we obtain like information, for example, on the temperature. So we know that, for instance, now, if there is like thermal electrons, they should go beyond 200 keV. But unfortunately, we're a bit limited yet. So we have to do something a little bit more. That is like, we don't know exactly what these particles are. We know they're hot, they're very energetic, where like there is like also, for example, magnetic field contributions or something else. It's a bit uncertain. But now I want to go back to the main question that I had at the beginning. That is, how can we push this to like very high pressures? With SZ, we can do easily, like as we're observing here. And this actually something we started to do. So this is like a collection of the systems for which we started to have result observations of the SZ effect that's basically tracking this transition between like this regime where we have no wide field measurements yet, and this regime where we start to see clusters. In the literature, generally this regime here above Redshift 2 is generally referred as the protocluster regime or protocluster beyond. And we want to understand what's happening there. So why we don't see anything there below, of course, like the sensitivity limits and the mass limit. And specifically, the point is, it's not working. Yeah, it's working. What we observe is that if you go in the literature, basically you have a lot of information on the galaxy population clusters, and specifically the file we see is like peak in star formation, peak of agent activity, and a potential connection to the environmental processing and effects on these galaxies and their activity to basically very quenched, very passive, big clusters at redshift 0. Of course, this transition cannot happen like out of nowhere, because immediately we have the ICM appearing and hot gas appearing. We should expect to see like the very fine states. It took us a while, but we managed to get there, and we actually did it on one specific target. It's a bit of the prototype, like the very example of a protocluster over density is evolving into galaxy cluster. So this is the spiderweb protocluster, and here is a composite image. You have HC in the background. Here, all this messy is part is the forming BCG. So it's like creating a lot of like companion galaxies and just creating also the gas from the surrounding. And here you have a very radio loud galaxy, of course, like we see in the radio jets. First of all, this is one of the ways for finding over density. So actually, this was like a good target to see what happened. What we did is that we pointed like a Z telescope and we measured a Z signal, which actually is the first time measuring a Z signal at these masses and at this redshift. We're talking here about a few 10 to the 13 solar masses and redshift 2.10. Why I'm measuring the mass because actually there's an interesting finding. So if you take what you can expect from velocity dispersion measurement, for instance, what we found is that the ST predicted mass, so the amount of thermal energy that should match with the realization prediction of a mass, always basically is always like smaller than this galaxy-based velocity dispersion. What this is telling us is not that this is wrong or that this is wrong. It seems that there is something going on. That basically it might be affecting our estimate. We don't know whether like we have a correct mass or not. What we might know though is that actually it is like a very dynamic process going on. These are from now like a few years ago, but it's a simulation of what happens to the mass here on the X versus like the Z signal through merging events. In yellow, you see basically mergers, and in white are the relaxations. We have like a different evolutions of the mass with respect to the ST, which means you might be either observing a very disturbed case where we had the mass already evolved and we're just seeing a biased perspective, or there is something else, like extra terms like non-thermal pressure and contribution that might affect this. But it was interesting because it was basically telling us, providing like a global hint that it was a very dynamic system. It actually is confirmed if you just combine the SZ measurements with multi-wavelength information. So first of all, we can see that basically the BCG and the forming central galaxies here, and most of the Z is actually on this side. An important caveat here is that the specific features you see are not real, probably just noise dominated. What matters here is like the global distribution. The second caveat is that what we might be seeing here is like a bit of a iceberg situation where we're just seeing the very high part of the iceberg, but then like on the rest is a bit skewed and it's like hidden little noise. But the peak is definitely like shifted with respect to the central galaxy, which means basically there's like something that is like moving the galaxy away from the pressure peak that should correspond to the gravitational peak. And if we add H alpha, Lyman alpha measurement there, we see this basically have a similar asymmetry, but on the completely opposite side. And what might be happening? We don't really know, mostly because we have limited information on the SZ and on specific processes affecting the SZ. But what's interesting is that, for instance, the radio jet is clearly showing a bending where you have the higher peak on Lyman alpha emission that is going the other way compared to the SZ, and also we have different behaviors of the two jets. And maybe what's actually we're observing is the very dynamic phase of accretion and evolution of this protocluster core. We need to do something more, of course, to learn more, what's going on. But for instance, what we did is that we combined once again SZ and X-ray to try to get something more out of it. The first thing you spot is that you can see there's like a bit of excess of counts. We have here in a very low count X-ray count regime here, but it's the same direction of the SZ asymmetry. If you combine SZ and X-ray, what we observe is that basically the thermodynamic profiles of this region are consistent with a strongly cooling core. It's very peak density profile and very low temperatures. So it might be that basically the star formation we're observing in the core of, and like true of course other tracers, is actually fed directly from the gases surrounding this galaxy. And basically we have the formation of very deep, cool-ish core. And this is not the only case where we observe this, but also we have other ancillary measurements. For instance, this one is another system. It's around a quasar, redshift 3. We basically have exactly the same signature. So we have strongly peaked X-ray emission, like it's just around the core, with like potentially like very cool gas being like compared to the real expectation, which might be telling us that overall, taken all together, that the evolution of this system is really happening from the inside out. So you first have the accretion of gas, and this start to cool and form a very structured core, and then you basically start adding up mass around it. Unfortunately, we have extremely limited information. So these are the photos which we have some measurements of the forming intercluster medium. And here the full dots are basically the one for which you have SE measurements and X-ray, and this one the one for which you have only X-ray. The issue with the one with only X-ray data is that that's not working animation. We both have very extreme luminosities that we measure, and if you convert it into masses, we have completely like the results are really hard to understand. But these rely heavily on scaling relations or calibrated on local systems, so we don't know whether they actually are holding this ratio. And the other problem is that if we go to the SE instead of measurements, we measure like a lot of like thermal energy and mass mismatch that might go in the same direction as the X-ray. The problem is that we can't really control if what we're measuring is consistent with just being like fully describing actually the presence of the whole hot gas. And for instance, we have very limited information on the baryon fraction and many things. So we're starting to build like add pieces of the puzzle. So for instance, the formation of these cool cores first, and then the larger scale structure after. But we need to see in the future what we can do. And the landscape maybe it's bright, maybe it's not. So we're here first, and there are going to be all of like wide field surveys is going to be up in the sky, but of course we have, for instance, like the negative news about like CNBS4, but we have also like high resolution like data that we're going to get in the future. And for instance, we're going to have new capable SE instruments. So like specifically, like we have extension to ALMA that I showed a bit. And also we have SKA. The SKA, of course, is going to be predominantly a radio facility, but it's going to reach actually high frequencies, high enough for actually measuring the Z. And here you can see basically two curves, like in solid white is the ALMA curve for the extended sensitivity array, or wide band sensitivity array, and then like in dotted is SKA. So we can really push down the sensitivity that we can actually achieve, actually measure more systems around this region here. The only caveat is that for SKA, but also for ALMA, the process of course we are getting to a regime where we start to observe also radio prime system with like galaxies, but also for instance radio halos and relics. So this is a bit of like a lower limit to what we can measure, and this is just an estimate for like 10 hours of integration on source. So it's a bit, and but not really long. And and there's a bit like a limitation. And the actual limitation is that they're both interferometers. So if you go back to the friendly bullet cluster, this is like the, once again, structural one, and this is where we pointed the ALMA at. If we just see how it will look like this, is a bit different from like what I've been showing with the X-ray measurement, like of this image here. The problem is that it's a heavily filtered perspective. It's like a high pass filter on the system. And even for SKA, the situation is not that great. This is like comparison, it's a simulated system, so we're like some distance to El Gordo. And this is what we can achieve with the first configuration of SKA, and this is what like will be the target configuration. You see all these ripples around here is just artifacts connected to how we don't observe large scales. And even there, it is better. So this is going to happen sometime after 2031, if everything goes fine. This might happen. So the one life might happen at some point, hopefully. So we have to do something more. We have to plan something better that can actually go there and actually measure what we need, which is like large scales and have also high resolution. And this is, for me, this is called Atlas. So once again, I'm pretty sure that Tony probably already introduced you a lot to Atlas and the concept. Very briefly, this is a planned 50-meter class facility. And there's going to be, of course, like a collaboration. The idea is that we really want to push like just a bit of outside of the SZ case for having a green facility. So really like going to be sustainable energy powered. But also it's going to be like a community facility, not just going to be for the SZ science. It's going to be very broad. So just consider that if you want to have like a large field of view and low sensitivity, Atlas is the way to go. For GSC, this was up, not expected. Right. For DSZ, why Atlas is going to be so great? So first of all, there's going to be a combination of advances compared to what we have now. We start from having broad spectral coverage. As I showed before, DSZ is a continuum effect. So of course, we really want to have a spectral mapping of the emission if you want to understand and disentangle the various components. We need large scales because clusters are big, as I showed like in the images before. We need high angle resolution, but also we need to go really deep and have like extreme sensitivities. This is Tony is what I stole from Tony. That is basically showing like how better Atlas is going to be when we combine the angle resolution that we can obtain with the field of view. So of course, like there is a compartment right in terms of like dish size. Atlas is going to basically beat all the other facilities that are planned for the moment in the same millimeter, like the same wavelength range by almost another magnitude. What about DSZ specifically? Again, like what I really care about. These are like the old plot. So this is once again the mass versus the mass versus redshift plot, and it's like the SA and ALMA curves. This is where we'll go with Atlas. So first of all, is that you can see here that it's going to be comparable to what we can achieve with ALMA, but you can imagine that this is going to be on the whole surveyed area, not just on very specific pointings. And the other thing is that we're going to win in this region. We're really going to push down the mass we can measure in here. And this is for a simple reason. With interferometers, you cannot measure large scales. Here, we're actually getting both. But I want to show you how this is going to be. Yes. This is stimulated cluster, relatively high redshift. This is what we can achieve with ALMA at the moment. So we can see something, but not much. So it's really hard to see. And this is what we can achieve for what I think is currently the best single dish facility we can use for SZ measurements. Once again, we can see probably a bit of the peak here, this region, but it's very limited information. If we point Atlas on that, this is what like the cluster will look like in SZ. So it's a net improvement, once again, in sensitivity, in angle resolution, and field of view. So I want to conclude. So my talk, once again, I mentioned that this is not just about SZ. So Atlas is going to actually is a community facility. So we're really thinking of it as a broad science-scale telescope. And these are like the main topics. So the idea is that we really want to plan to have Atlas for really going there and studying all the variants that are there, not just the hot gas, but also to combine the fact that we can measure together the hot and cold component at millimeter wavelengths. We're really interested, of course, in understanding how the environmental evolution like really brings our structure from the first fluctuations to what we observe in the universe, but also it's really going to be great for transient science. So it's going to do that. And if you want to take a look, actually, I forgot to put the QR code, but we have a collection of science cases that we developed in the past years, and they're collecting this Open Research Europe collection. And I want to conclude with a bit of a summary, so just to leave a bit of questions, if there is any. That the point is that we're in a transition period where we really started to use DSZ for studying galaxy clusters in what I like to say in a way is basically complementary, but also similar to what I've been doing with the X-ray observations. The great advantage is that we really have virtually no limit in redshift for like the same properties of DSZ itself. And it can really bring a comprehensive understanding of the physical and thermodynamic properties of clusters, but also galaxies, and hopefully in the future, like filament and large scale. And the ICE future is probably bright enough because ALMA extension, but also escape, then hopefully and ultimately Atlas will really just open like a new millimeter window on evolution of the channel of the hot universe. And with this, I'm done, and really thank you very much for your attention.
Thanks a lot. That was really great.
Thank you.
Do we have any questions from the audience? Or can I start? I'll start. You mentioned at some point scaling relation that you use them to input the math from the X-ray observations. Can you elaborate a bit more on what are the assumptions done and to what extent applying this relation that redshift about 2 is a shaky?
Yeah. So like the basic, for instance, relation is temperature luminosity one that we obtain from like local systems. So first of all is a mass regime, the mass domain. So we mostly tune this on very massive galaxy clusters in the local universe. So even if you assume that the physics is the same, it remains the same, and also that the scaling are applied, the point is that as you move to lower masses, you might have different effects getting in to like different feedback processes, but also accretion and merger activities. It can make your kind of like push your gas like away from realized or nearly realized state. So the lower the mass, the easier it is to kind of shake the structure. But at the same time, the higher is the redshift, the higher is the rate of merging systems, but also, of course, of unstable gas. So you might be able to get into a regime where your tight correlation doesn't hold because the main assumption, like the kind of just like the realization of your system is not really valid, or it's like it deviates too much from real. So that's one very basic example. But then, of course, the point is that we don't know whether the scaling we derive, like self-similar assumptions, really hold beyond a given redshift. And also, this is something we have been testing mostly with very massive systems. I mean, so as I showed before, of course, we kind of have a 10 to the 14 lower limit across the whole cluster range. So that's also something that should be tested to understand how much the scaling relation can go down in terms of like mass in the same way. So this is the bit, and also selection functions, and there's a many kind of effort for that. Right. But this is mostly like one of the main problems.
And especially the higher the redshift, the larger the probability of having large scale accretion. That will also formalize the system.
Yeah.
But could you educate this scaling relation with the MG models you showed, for example?
I think that I think so. The problem is probably like right now specifically is that we really have this extremely limited view with like having 4 targets is really like hard to kind of tune it to like kind of calibrate on that. There's an extra problem that I kind of like decided to hide like under the carpet is the definition of photocluster is extremely heterogeneous. So it is not like galaxy cluster is kind of like easier to identify and define. So like the large structure is the mostly realized like gravitationally bound. Under the name of photocluster, you have a lot. So it could be like systems that clearly show like a high overdensity of galaxies around a radio loud galaxy. That's so this kind of piling up energy and helping kind of not letting the gas cool too much. But also you have very sparse overdensity of galaxies. And so applying all the same scaling relations on these different systems and or the other way around, using this very different cases for like calibrating one relation might be a bit of a stretch. So and hard to generalize. So I think we have to first go there and understand whether there is any difference between these different clusters or not, whether it can be considered as a whole as proto clusters or like forming clusters. And if there is not, then we can calibrate if there is any difference to see how well we can kind of add simply scatter the relations or just do something else. So yeah, a lot to do.
Any questions? Yes, please.
It's a bit off topic, but so you showed that Atlas and very good for analysis. So I was wondering, have an idea of how it's going to perform in terms of the kinetics?
Yeah, no, actually, that's a very good question because I didn't include the plots extremely well. I have to say, in terms of sensitivity, we can measure actually in principle the KSZ component from like even individual parts of a cluster, of a master cluster. The main problem is mostly component separation issue. So that's something we cannot really beat because the sort of KSZ signature are the same as the CMB. So on small scales, I think we have like a bit of troubles of understanding this. Let me say that we can turn this into a positive direction. That is, we have to develop methods for like separating what is CMB, statistically speaking, of course, to what is actually KSZ. But truly from a sensitivity perspective is great. Like we have Compton-Y sensitivity, effective KSZ Compton-Y of 10 to the minus 6, 10 to the minus 7. Do you remember exactly? I think somewhere in the range of below 10 to the minus 6. So
it depends whether you go wide or deep, but yeah, it's easy
somewhere.
to get to.
So we have to kind of like spend a bit of energy in understanding how we can really distinguish like a very cold spot, CMB cold spot from KSZ cold spot. But yeah, so glad to have inputs if there's any. And
I guess if I can just add, as we go to higher and higher redshift, where the most interesting stuff is, like the KSZ will be easier to separate on smaller scales intrinsically anyway, right? Like the objects are small, all of that.
Yeah.
Because the CMB goes down so easily.
Right.
Relating back to Martin's talk last week.
Hopefully we'll get more from individual systems. So,
and then relative direction.
Right.
So we can get temperatures without cost check.
So yeah, now we're discussing specifically like just to add a bit like that whether like we're able to reconstruct like temperature profiles and pressure profiles jointly just with the Z measurements, because they're detaching completely from X-ray data. Of course, like having the complementarity is still useful for checking that everything is fine, but also getting like a bit extra information. I mean, we can turn the complementarity into Abel parameter or like a line of sight extent or clumpness, like and everything. That depends on what you're interested into. Actually, the more information we get from the Z, the better is going to be like the better chance we have in actually using this and for like extending what we can do with clusters, individual and as a sample.
Just out of curiosity, does the magnetic field has an impact on the shock cooling? For example, on the bullet, you mentioned that different temperature, the different component. Can you constrain the magnetic field with this such shock modeling?
So that's a good question, and let me say I don't know, but let me like turn it into like something I found extremely interesting. So the bullet cluster specifically is considered as the textbook example of bow shock. And if you go, so magnetic fields like with these measurements specifically, it's hard to get like an information because they're sensitive only to the thermal component. So it's if you have to have extra information on either like the extra pressure, the total pressure in the system, or on something else that is, for instance, from like radio observations. If you go to the radio, the kind of standard description is that you have that radio relics freeze shock fronts, especially in the outskirt clusters. If you just combine all this information, you see that actually the bullet doesn't have relic at the shock front, and actually see a very precise, very like kind of defined shock-like features in the radio halo. So I think that like just as Z and X-ray cannot provide information on any field, but combined with radio information, specifically with like what you can know from like turbulence, acceleration and stuff, I think can be extremely powerful never been done, mostly because we don't have a good model for really connecting everything together. But I think actually the bullet is one of the places where we can actually try this. So yeah, hopefully actually soon.
Do you expect a role in the realization of the clusters? Not much.
I guess probably like in maybe keeping it from actual realization, because so on average it can be like extra pressure on small scales, but also I think can kind of prevent the kind of the buildup of the thermal pressure in like like turbulence, and I'm not entirely sure like how that will affect the turbulence distribution, but yes. So I think my understanding is that it can actually prevent it slightly, and it will just add to the slight deviations we observe from pure realization.
Question again. All right. Well, let's thank you again.
Thank you very much.
Please wait for Lucas with the pizza.